When people first learn how a CPU works, they usually hear about fetch, decode, execute, and write back. But in modern processors, there's one more stage that matters just as much: commit, also called retirement. And this stage is the reason an out-of-order CPU can look chaotic on the inside while still appearing perfectly orderly to software. So in this video, we'll answer a simple question. What does it mean for a CPU instruction to commit? Why can't execution alone be enough? And how does the processor stay precise, correct, and recoverable even when hundreds of instructions are in flight at the same time? Let's build this from the ground up. A modern CPU does not necessarily execute instructions in the same order they appear in your program. Instead, it tries to find work that is ready right now. If one instruction is waiting for data from memory, the CPU does not want to sit idle. So it looks ahead, finds other independent instructions, and executes them early. That is called out-of-order execution. And it is one of the main reasons modern processors are so fast. But this creates a problem. Your program expects instructions to behave as if they happened in program order. Instruction 1, then instruction 2, then instruction 3. Software does not want to see the CPU's internal shortcuts. It wants a clean, predictable machine. So here is the key idea.
Instructions may execute out of order,
but they must become official in order. That moment when an instruction's result is finally accepted as part of the architectural state of the machine is called commit or retirement. To understand why this matters, we need to separate two ideas that are often blurred together.
Execution.
En kan het panel på dat de project might sex and the tobin say to also associational tobin say tortive and at the tobin set to straight and set tonilla to bloody when fan cured. Of dies to misuse of beyond so starting in that setting to bar tritson. Also seeing words of your equation trusting doctrine and tutor say to you and this based and the teachers level they to observe the con map Emma they give a trap the cinches and topic control can commit. Execution means the CPU has done the work. Maybe it added two numbers, maybe it calculated an address, maybe it loaded data from cache, maybe it even finished a multiply that started several cycles ago. But at that point, the result is still temporary. It exists inside the CPU's speculative machinery. It is not yet visible as a final guaranteed result. Commit is different. Commit means the CPU is now saying, this instruction is complete. It is valid. All older instructions before it are also valid.
No exception or misprediction before it needs to roll us back.
So now its effects become permanent. That distinction is everything, because modern CPUs speculate. They guess branch directions. They execute instructions before knowing whether those instructions should really have happened. But they read registers using renamed mappings that may later change. They may even begin work on instructions that will eventually be discarded. So the CPU needs a checkpoint between work has been done and the machine state officially changes.
That checkpoint is retirement.
Let's make this concrete. Imagine your program has these instructions. First, load a value from memory. Second, add one to it. Third, store the result. Fourth, divide another value. Now imagine the divide is slow, but the store address is ready early. An out-of-order CPU may execute parts of later instructions before earlier ones finish. Internally, this is fine. But what if that divide triggers a divide by zero exception? Software expects the CPU to stop at exactly the faulting instruction, not after some random later instruction has already changed memory. That requirement is called precise exceptions. And retirement is what makes precise exceptions possible. The CPU delays making results official until it knows it is safe. So even if a later instruction already executed, it cannot commit before all older instructions have committed first. If an older instruction faults, the processor throws away younger speculative work. From the software point of view, it looks like the CPU was executing strictly in order all along. That illusion is carefully maintained. Now let's talk about where instructions wait before they retire. This is where the reorder buffer comes in. The reorder buffer, or ROB, is one of the central data structures in an out-of-order CPU. When instructions are decoded and dispatched, they are placed into the reorder buffer in program order. Think of it like a long queue that remembers the original order of the instruction stream. Each entry tracks things like what the instruction is, whether it has finished executing, whether it caused an exception, and what result it produced. Now, here is the important part. Instructions can finish execution in any order, but the reorder buffer retires them from the front one by one in program order. So if instruction number 8 finishes before instruction number 5, that's okay. Instruction 8 just waits. It cannot retire until 5, 6, and 7 have all retired first. This is how the CPU gets both performance and correctness. It gets performance from out-of-order execution. It gets correctness from in-order retirement. Now let's connect this to architectural state. The architectural state of a CPU is the state that software is supposed to see. That includes things like architectural registers, program visible flags, the program counter, and committed memory updates. But internally, the CPU often keeps many more temporary values than the architectural model suggests. This is especially true because of register renaming. With register renaming, the CPU does not immediately write results back to the small set of architectural registers like RAX or X0 or whatever the instruction set defines. Instead, results usually go into physical registers. These are part of a larger pool of internal storage. Renaming breaks false dependencies and allows multiple in-flight instructions to produce results without stepping on each other. But if the CPU is using temporary physical registers, how does software still see a simple architectural register file? Again, retirement is the answer. An instruction may compute a result into a new physical register early, but that result does not become the official architectural value until the instruction retires. At commit time, the CPU updates the architectural mapping so that this physical register now represents the current committed version of that logical register. In other words, execution creates a candidate result. Retirement makes it official. This is why retirement is sometimes described as the point where speculation ends for an instruction. Before retirement, the instruction is provisional. After retirement, it is part of history. Now let's talk about branches. Branch prediction is another reason retirement exists. Suppose the CPU encounters a branch. If something is true, go left, otherwise go right. Waiting for the actual branch result would stall the pipeline. So the CPU predicts which way the branch will go and starts executing instructions down that path. If the prediction is correct, great. The CPU saves time. But if the prediction is wrong, then all the younger instructions on the wrong path must be discarded. That only works if those instructions have not committed yet. They may have executed, they may have consumed energy, they may have filled queues and registers, but they are still speculative.
So when the misprediction is discovered, the CPU flushes them.
The machine rolls back to the correct point and continues from the proper path. Retirement is what separates speculative and discardable from permanent and visible. Without retirement, branch misprediction recovery would be far more difficult. Now let's go deeper into exceptions and faults. Suppose an instruction causes a page fault, or a detection fault, or divide by zero, or an invalid opcode trap. The operating system expects the CPU to report the fault at the exact architectural instruction that caused it, not after younger instructions have already modified the visible state. This is called precise state at the fault boundary. And precise state is one of the biggest reasons the retirement mechanism exists. The CPU may allow younger instructions to execute early, but if an older instruction eventually faults, the processor can stop retirement right there. Older instructions have already retired, so they are official. The faulting instruction is identified exactly. Younger instructions have not retired yet, so they can be discarded safely. That gives software a clean, precise snapshot. This is not just a convenience. It is fundamental to how operating systems, debuggers, and exception handlers work. Now let's talk about stores, because memory makes this even more interesting. A store instruction writes data to memory, but in many CPUs, a store does not update the cache or memory system immediately when it executes. Instead, it often writes its address and data into a store buffer. Why? Because stores must also respect retirement order. If a younger store reached memory before an older instruction faulted, software could observe an impossible state. So the CPU usually lets the store execute enough to prepare its data, but delays making the memory write globally visible until the store retires. That way, memory updates follow the same rule as register updates. Speculation first, commitment later. So when people say retirement makes results architectural, that includes not just registers, but also the point where stores become officially part of program-visible memory order. Now, depending on the CPU design, the exact moment a store becomes visible can be subtle. There may be layers involving the store buffer, cache coherence, and memory ordering rules, but the core principle remains the same. A speculative store cannot be allowed to become architecturally visible too early. Retirement keeps that under control. Now let's look at a simple timeline. Imagine 4 instructions enter the machine in order: Instruction 1, Instruction 2, Instruction 3, Instruction 4.
Instruction 1 is a cache miss, so it takes a long time.
Instruction 2 is a simple add, so it finishes quickly. Instruction 3 is another simple arithmetic instruction, also quick. Instruction 4 is a branch, and it resolves quickly too. Internally, the execution order might look like this: 2 finishes first, then 3, then 4, finally 1. But retirement still looks like this:
First one retires.
then 2 retires, then 3 retires, then 4 retires. Or, if 1 faults, then retirement stops at 1 and the younger completed instructions are discarded. That is the whole model in one example.
Finished does not mean committed.
Executed does not mean retired. Ready does not mean architecturally visible. Now, let's address a question that often comes up. Why not just update the architectural registers immediately and somehow undo them later if something goes wrong? The answer is that rollback would become much more complicated. You would need a way to restore old register values, undo memory writes, recover flags, fix control state, and unwind speculative side effects. That gets messy very quickly, especially when many instructions are executing in parallel. So instead, modern CPUs often use a cleaner approach: keep speculative results separate from committed state and only promote them at retirement. This makes recovery much more manageable. If something goes wrong, discard the speculative work.
If everything is fine, retire in order.
That is a much more controlled design. Now, different CPU architectures and microarchitectures implement retirement in different ways. Some use a classic reorder buffer. Some use more distributed structures. Some separate register commit from other forms of bookkeeping. Some aggressively optimize how many instructions can retire per cycle. But the high-level idea is the same across modern out-of-order designs. Execution can be speculative and out of order. Retirement is authoritative and in order. And that last part matters for performance too. Retirement bandwidth can become a bottleneck. If a CPU can execute many instructions per cycle, but only retire a few per cycle, then completed work can pile up behind the commit point. That means the front end may eventually have to slow down because the machine cannot free old resources fast enough. So retirement is not just a correctness mechanism. It is also part of the throughput story. A wide superscala core might retire 4, 6, or even more instructions per cycle, depending on the design. That retirement width affects how quickly the machine can turn speculative progress into real progress. This also connects to resource recycling. When an instruction retires, the CPU often knows it can finally free certain older resources. For example, in a renamed register design, once a new register mapping becomes committed, the older physical register that used to hold the previous architectural value may eventually be released. Similarly, reorder buffer entries can be freed. Load store bookkeeping can move forward. The machine advances its safe frontier. So retirement is also the stage where the CPU says, this instruction is no longer a risk. Its resources can now be reclaimed. Now let's summarize the big picture. A modern out-of-order CPU has 2 personalities. Inside it is aggressive, speculative, and opportunistic. It executes whatever is ready. It predicts branches. It renames registers. It overlaps long latency work with short latency work. But from the outside, software sees something much calmer. Instructions appear to complete in order. Exceptions are precise. Registers change in a coherent way. Memory updates follow the architectural rules. The mechanism that connects those 2 worlds is retirement. Retirement is the moment an instruction stops being speculative and becomes official. It is the boundary between internal execution and architectural truth. So the next time someone says a CPU executed an instruction, remember that may not mean the instruction is done in the way software cares about. In a modern processor, the final word belongs to commit or retirement, because in the end, execution is only a proposal. Retirement is the decision. And that is how CPUs stay fast without becoming chaotic.